So I'm sick of talking about standards and policy, so we're going to do some mathematics. So we have a triangle on the left here, has perimeter 12 and area half times base times height, 2 times 3, that's 6. Triangle on the right, it has perimeter, okay, we're going to do adding fractions now. I left this denominators of 15, 21, and 35, that's 3 times 5, 3 times 7, and 5 times 7, so our common denominator is 105. 7 times 41 is 287. 5 times 101 is 505. 287 plus 585 is 792. 3 times 156 is 468. So we're going to take that 8, put it with the 792, get an 800. Plus 460. Yeah, I know. Plus 460. 1260 divided by 105 is 12. Same perimeter as the 3, 4, 5 triangle. Now what about the area of this triangle? Well, how do we get the area of a triangle with all these weird irrational sides? We use Heron's formula. That's a formula that gives you the area of a triangle in terms of the lengths of its sides. It's a beautiful formula. Notice the patterns there. I've got like a plus b plus c. Then I'm going to put it, oh well, forget about it. Anyway, let's if you think I'm going to do that in front of you, you've got to be joking. So Wolfram alpha, however, can do it for me quite nicely. It says the area of this triangle is 6. Same area as the 3, 4, 5 triangle. So how do we do this? We look at the incircle of the triangle. Incircle is a nice way of parametrizing triangles. I'm going to take those angles, alpha, beta, and gamma, alpha, beta, gamma, and use those to parameterize the triangle. I want to find a way of figuring out how to construct that beautiful example I just gave you. So first, there's a relationship between the area of a triangle, the radius of the incircle, and the perimeter of the triangle, which you get just by adding up half base times height around this triangle. Each of these triangles has base on the perimeter. Half the perimeter times the height is the radius. Add them all up. You get half the perimeter is equal to the area. Half the perimeter times the radius is equal to the area. But in our case, 6 is half of 12, and so our radius of our incircle is 1. Okay, so what that means is that if I want to get area 12, area 6, and perimeter 12, I just need to get the perimeter equal to 12, which I will do with this construction here. Maybe I'll let you do it. Okay, at least the alpha shows up. Tangent of alpha over 2 is this over the radius, but the radius is 1. Therefore, the tangent of alpha over 2 is this plus this. That makes 2 of them. There are 2 of the other ones as well, 2 of the gammas. So in order to make the area 6 and perimeter 12, all I need to do is to make the sum of tangents equal to 6. Isn't that amazing? Just like adjust that triangle with the alphas and the betas and the gammas. As long as you keep the sum of these tangents equal to 6, you're okay. Of course, no one knows how to solve that equation, so let's make it into an algebraic equation by choosing variables x and y to stand for the 2 tangents. The third tangent can be expressed in terms of x and y by a trigonometric formula, which is left to the reader as an exercise. And so I get this beautiful algebraic equation. So just pause for a moment, and I've multiplied through here. This equation is an equation in x and y, which I can plot in the xy plane. Every single point on this curve, actually just this part of the curve is all that counts really. Every single point on this curve gives me a triangle with perimeter 12 and area 6. So for example, if I take these 6 points, they all give me a triangle. In fact, they all give me the same triangle. They all give me the 3, 4, 5 triangle. There are 6 points for every triangle because there are 6 ways I could have labeled all the sides A, B, and C. But still, how do I find more points? What I do is I draw a line through 2 of the points and get a third point over here. You know, this is easy. You can do this on the back of an envelope in an airport. Then I draw a line through this point to another point over here, and I get this point. I actually did this on the back of an envelope in an airport, believe it or not. This point here is a triangle, corresponds to a triangle. If you backtrack all the things I just said, you will find that triangle, and that's that wonderful triangle that I gave you at the beginning, a rational triangle with rational side length, rational area, same side length and area, and you can do this at home. You can construct your very own by just draw more lines. You can have infinitely many rational triangles, rational side length, rational area, which have area 6 and perimeter 12. So there's a beautiful article about this in Mathematics Teacher. This is just to prove that I wasn't going beyond the scope of this talk by talking about this. And it's by Steve Rosenberg et al. And take a look at it to find out more. Thanks.